Alrighty, good morning, everybody, and welcome to the wolfSSL live webinar on DTLS 1.3 with wolfSSL engineer Marco Oliverio. My name is Kajal Sepkoda, and I will be moderating this webinar. All attendees will be in listen-only mode. If you have any questions, please feel free to use the Q&A box or raise your hand to be unmuted if you'd like to ask the question live, as we will host a Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation, and I invite everyone to follow us on Twitter at wolfSSL, as well as all of our other socials. Please feel free to email us at facts@wolfssl.com if you have any additional questions. And now I'd like to give a brief company overview before we move on to the technical presentation. wolfSSL was founded in 2004 by Todd Auska and Larry Stefanik when they realized there wasn't an open source, dual licensed embedded SSL library available. OpenSSL existed at the time, but there was a demand for an alternative that was easily portable, smaller, faster, available under a clear commercial license, was equipped with a clean and modern API, and offered commercial-style developer support. wolfSSL was born into this market need with an OpenSSL compatibility layer. Today, wolfSSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of almost 50 dedicated employees in 2022, most of which are engineers. This progress is, of course, supported by a strong partner network that we're very proud of, which includes DDCI, STMicro, and RTI, for example. Since the beginning, our engineering team have developed several embedded security products, including wolfCrypt with the DO178 support, FIPS certification, and a FIPS-ready offering, MQTT up to the version 5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfboot, as well as Java wrappers and JSSC support, and commercial support for curl. All of these offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. And now I'm going to hand it over to Marco for the presentation.
Thanks, Kajal. Hello, everybody, and thank you for joining this webinar. I'm Marco Oliverio. I have PhD in computer science. I'm specialized in low-level computer security, and I'm a software developer at wolfSSL. In the last month, I worked to the implementation of the latest version of the datagram transport layer security. That is the version 1.3. That's the main topic of this webinar. Just in one sentence, DTLS allow in a very easy way to provide security to applications that communicate using datagram-based protocol. Let's see what will be our agenda today. So we'll start for a little bit of background and basic on why we need DTLS, how the DTLS works, and so on. Then we will see some difference between the latest version and the old version. Then we will see how to build and start experimenting with the wolfSSL DTLS 1.3 implementation. We will also see what are the code changes you need to apply to transform a simple client UDP application to use DTLS. And then we will have a Q&A session. So let's start to see why we need DTLS. So and of course, I firstly want to show you the main product of wolfSSL, that is the wolfSSL library itself, and this is where DTLS is implemented. It's a lightweight, really portable, and C-based library. It's up to the latest standard, up to TLS 1.3. It's very small in footprint. It's like 20 times smaller than OpenSSL. So it's really aimed to be used in embedded device. We support a lot of operating system, microcontrollers. We can also run it bare metal on very tiny microcontroller. So let's start with why we need to use DTLS. So TLS is already a protocol that provides security guarantees. But there is a problem with TLS. The main problem is that it requires reliable and ordered communication channel. This means that every message that is sent to through this communication channel need to be delivered, and also that the order of the message need to be preserved during the communication. Usually it's TCP that guarantee these two characteristics to TLS. So why this is a problem? The problem is that to guarantee these two things, the protocol needs to do a lot of housekeeping, need to do some buffering of message, need to add explicit acknowledgement, retransmit packet if they get lost, and so on and so on. And this introduce overhead. Overhead, especially in the latency, in the minimal time you need to spend to start the communication, and or the amount of bandwidth you will use during the communication. So, and also you will see some spurious delay. So the problem is that, the point is that there is a lot of application that really don't care about losing a packet from time to time or having this packet in the wrong order, but they really cannot afford this type of delay or this type of overhead in latency and bandwidth. Typical example of this type of application are real-time streaming application, online gaming, or a battery-powered device that sleep for a lot of time, and when they wake up, they just want to spend the minimum amount of bandwidth to save battery. So all this kind of application usually don't rely on on communication channel with this type of semantics, but they usually use UDP protocol that is more lightweight. You just send and receive data without these guarantees. And this is the main idea about DTLS. It's just the set of minimal delta change to TLS to make it working over datagram protocols as well. These are two main advantages. The first one is that you will reuse a well-established and studied crypto system. You will not reinvent the wheel, and with the so you have less opportunity to insert new vulnerabilities. And also you will reuse most part of the current TLS implementation. So this will be a quicker implementation of DTLS itself. So how this works? So basically, TLS needs this reliability and ordered, because there are a set of messages, especially in the handshake, that really needs to be delivered and really need to be delivered in order. Also, in TLS, you see when TLS decrypt data, you see the full stream of data, and so you always know which part of this ideal stream is decrypting. While with DTLS, you will have holes or reordering, so you really don't know which part of this ideal stream you are decrypting. So DTLS solves these two problems by adding some retransmission and reordering feature, but only for this message needed for the setup of the cryptographic session. In reality, also some other control messages are retransmitted and reordered as well. And also it do an explicit number of the message. So you use explicit sequence number to allow the decryption routine to always know which part of this ELA stream they are decrypting. It's important to note that DTLS does not provide neither reliability, neither ordering for the real application data. Because the application data follows the same semantic of a lightweight protocol. And this is, of course, obvious, because otherwise you will incur in the same overhead as we talked before. So just to do a brief recap, when DTLS is a good idea, it's a good candidate when you have to secure a UDP-based application that you are using real-time data communication. You have tight resource limits. You want to use a lightweight protocol, or you want to send a large amount of sensor data and just to save on your bandwidth. So now that we see what DTLS is and how it works, let's see a little bit of history on DTLS implementation and their version. So the first version 1.0 was based on TLS version 1.1. But when TLS version 1.2 will get published, they decide to skip the number to keep the version numbering in sync between TLS and DTLS. In the 2018, TLS version 1.3 was published, and now after 4 years, we have the latest version, the main topic of this webinar, DTLS version 1.3, that was published in the RFC 9147. So yes, the TLS was final certification was published just in this April. We are really excited. We are, as far as we know, the first functional implementation, and it's really nice to be so early adopter of new technology. So let's see where DTLS will fit in the protocol stack of typical device. Here you see a device that is using unsafe communication. You see this kind of device usually collects some data from sensor or need to send some communication configuration. So they frame this data in a proprietary protocol, and then they just send by UDP. Of course, this device will work, but it will not use any, the communication is totally unsafe. And nowadays in the market, this kind of device are really out of place, because with all the privacy concern, all the compromised concern, you need to save your communication. So, and this is where DTLS came to the rescue. And this layer that is just on top of UDP, and it provides you with three very important security guarantees. The first one is authentication. So the partner you are talking to is for sure the intended one. You are sure that it is the intended one. It provides confidentiality, so the content of your communication is hidden from third party, even under interception. And it provides you with the ability to detect some tampering of the data, so it provides you with integrity protection. So now that we saw more or less what is DTLS and how it works, let's see some comparison, what's new in this new 1.3 version. So I think the major point is that DTLS version 1.3 is based on TLS version 1.3, so it brings all the improvement of the latest version of TLS. This will mean a more modern, a faster, and a safer crypto. We will see each of these. So it's safer. First of all, it removes a lot of unsafe algorithms and encryption methods from the attack surface, basically. All these algos listed in this page are known to be weak, or some attacks were discovered and are completely eliminated from the standard. The last one is a way of using AES, and it was prone to a lot of attack, and so this was also eliminated. But it's also safer because, especially during the handshake, almost all the handshake, so this beginning part of the connection when the cryptographic section is set up, is encrypted. We can see with a comparison with the handshake in the 1.2, you can see in this diagram that the client sent the client hello, and the server just replied with a bunch of message. Then the client sent another bunch of message, and then a finished message, and only this finished message is encrypted. And again, from the server side, only the finished message is encrypted. And this is the handshake in the version 1.2, both for TLS and for DTLS. In the version 1.3, instead, there was a complete rearrangement of the handshake. As you can see, the client sent a client hello, the server replied with a server hello, but after that message, everything is encrypted. Notably, is encrypted certificates are encrypted, and this is a large step ahead in the for privacy, because certificates can disclose the identity of the communication partner. It's also safer because it's enforcing that every new session has a new key, and this guarantee you with perfect forward secrecy. Without PFS, you will be susceptible uh, of third party that want just to harvest all your data, store them, and then they hope to get hands on your private key. They hope that your private key gets compromised, and then decrypt your data, your past data they stored in the past. But using some kind of ephemeral key every time, you are protected from this kind of attack. There is an asterisk there because there is still a way you can use pre-shared key that do not enforce perfect port secrecy in DTLS 1.3. And because there is always a trade-off in getting a new key and getting a faster handshake. But it's also modern because the only cipher mode allowed in TLS 1.3 is the authenticated encryption with associated data, AEAD mode. This mode is a way of encrypting that simultaneously encrypt the data but also authenticate the data in a single operation. This is really important because in the past, doing that as two operation, doing that in two operations really difficult and prone and error prone. And there was a lot of attacks when these two operations were combined in the wrong way. It's also modern because they use newer algorithms with smaller key size, and this allow you to firmware image that are smaller than before. But, and this is, I think this is very cool. It's really is faster than the older protocol. It's faster in the amount of time you have to wait to start sending encrypted data. Let's see, in the 1.2 handshake, this diagram is really similar to the one I showed you before, but I highlight where the client send a client low, the server reply with all this bunch of messages. So you see that you have a message from one side to the other, and then some message from the other side back to the other one. And this is the time spent to do this ping pong is referred as round trip time. And you see that there's one round trip time after this exchange of message, and then the client send another bunch of message and the server reply back. And only now they can start to exchange encrypted data. So they can start to exchange encrypted data after 2 round trip time. In the 1.3, instead, there was a full rearrangement of the handshake. So you can see there is the first round trip time when this client send a client low, the server reply back with server low and a bunch of other message. Then the client send back certificate verify and finish it, but they can just start right away to send encrypted data. So you can start sending data basically half the time before that the older version. To be precise, the server can do even better, can start to send data even just after he send the finished message, so in 0.5 round trip times. But this should be done with some the server should be quite careful because you don't yet have authenticated the client. You don't know if the client is really alive or is that spoofed packet, and is not really used because usually it's the client that need to say something first. So it's the first one to send application data to the server. And in this graph, you can see how much you can gain. Of course, this depends how much network latency you have, how much time it takes for you to make these round trip times. But you can see that the gain in speed of the handshake is basically remarkable. It's also improved the resumption. The resumption is the feature that you don't want to repay the overhead of the handshake for every new connection. So when you pay that for one connection, you exchange some cryptographic material that allow you to start another connection either in the same times or in the future without paying the price of doing another handshake. And a very, very cool thing is that when resuming, you can start sending application data directly from the start. So zero RTTT time. This is also known as early data. It's a cool feature, but again, there is a trade-off with the security because it does not guarantee perfect forward secrecy and can also be susceptible of replay attacks. And all this that we saw in the last slides were improvements that were just bring it in by rely on TLS 1.3. But there were also some improvements that are DTLS specific that make this version of the protocol safer, faster, and more efficient. First of all, this explicit sequence number that are on the packets now are encrypted, while in the version 1.2 they weren't encrypted. This again allow some traffic analysis attack, and also it makes some replay attacks harder to carry. It's also very, very super efficient record header format. They change the header, they make it a little bit complex, but this you now have this kind of variable length unified header, but can be as little, as small as 2 bytes. So you will have only 2 bytes of overhead in your communication coming from the header. They also introduce explicit acknowledgement message. And this is important because it allow a partner when a disruption in the network is detected to communicate with the other people which kind of message were received, and just to ask for a transmission only for the one I don't have. As an example, here we see the client that just sent some message and one of them get lost. The server detect a disruption and just sent explicit message saying, I got the yellow one, I got the blue one, and the client just sent the orange one. So this saves bandwidth, but it's also faster because otherwise the client that has some timeout will have to retransmit the whole flight and only sometimes later. So this is faster and consume less bandwidth. And also there is another very nice feature that is connection ID. This is not really in only in DTLS 1.3. It has also an RFIC on its own and can be used as an extension DTLS 1.2. But it's built in 1.3, and this is very nice. And what is connection ID? It basically you will use a label that you can attach with your on the packet, on the message, or your connection. So you will not rely anymore on the IP address or on the source or destination port to identify which connection a message belongs to. So you are basically decoupling the IP address for the connection. And these are two main use cases. One is just multiplexing multiple devices using the same IP address and source and device port. But also there is another one, is that there's this use case where you have a lot of these IoT devices that they are going to sleep for a lot of long time, then just they wake up, send some data, and then they want to come back to sleep. So they don't want, when every time they woke up, they don't want to do a new handshake. So they want this very long lasting connection. The problem is that when they are behind a NAT and you wake up, your IP address may be changed. So you are kind of forced to do another handshake. So, but using connection ID, you can avoid that. Of course, DTLS 1.3 supports version negotiation, so client server can optionally support both version of the protocol, or even can support 1.0, and this allows you to gradually upgrade your ecosystem. Peers with different versions can coexist, and then they will just negotiate the highest available version for both peers. So now that we see, now let's start to play a little bit with the DTLS 1.3 and with the wolfSSL implementation, and start with get our hands dirty. So to build configure the wolfSSL with DTLS, you need first to clone the repo. You enter in the directory, you will run autogen.sh. This will just create autoconf tools. And then you start with configure. You need to provide these two flags, enable DTLS and enable DTLS 1.3. And then you can just make this. After that, if the after building it, you will have two examples, a server application and a client application. And you can force them to use DTLS by providing the -u option that tell them the example to use DTLS, and then to provide me a -v4. This is to tell the application to use version 1.3. These examples are are full of other features. Just try --help to see all of them, and try all of them as well with DTLS 1.3. Once you run this application, we will see an output similar to this. You see that the negotiated version will be DTLS 1.3. You can see also that the cybersuite used is an AEAD cybersuite AS GCM, and also there was key agreement based on elliptic curve, and then there are two messages that the application exchange. If you try to dump this connection, you will not get too much from Wireshark. This is because Wireshark didn't really support yet DTLS 1.2. We just saw that it was published in 1.3. And also, even if it was supported, the end chain is encrypted. So to decrypt the packet, you need to provide the key in Wireshark. That is something that is not yet supported. Still, you can examine the server LO, and in the server LO, you can see that the cyber suite chosen by the server is an AEAD cyber suite with the first byte is 13. That is the byte reserved for TLS 1.3 and DTLS 1.3 cyber suite. That will use elliptic curve. Specifically, now we are using the 256 P1 curves. And then also you see in the advertised version that you will advertise the DTLS 1.3 version. That, of course, Wireshark didn't recognize yet. You can do a comparison between dumped and shake with TLS 1.3, providing the key, and DTLS 1.3. You will see that there are some difference. First of all, the certificate was fragmented to enter in the maximum transmission unit. And also, you need an explicit hack from the server to acknowledge the finished message of DTLS 1.3. So now just start to see how to use DTLS. So we have how to make a simple UDP client use DTLS. So taking something that have a protocol stack like the one on the left, and just to add DTLS to that. The adaption code change will go just on top of DTLS, and after you already framed your data with your proprietary protocol. So this is an oversimplified version, simplified UDP client. You will see that you create a socket, and then you start sending and receiving data, and then you close the socket. So first of all, you need to do some setup. So you have to create a new wolfSSL context. This object will store common information to all the session, and you will provide as an argument wolf DTLS client method. Then you need to load the root certificate authority certificate, and this is needed to authenticate the other peer. And then you will create a secure SSL object. This is the object that will store session-related information. Then you will go ahead, create your socket, but after that, you will associate the other peer address to the SSL object with DTLS set peer. So you are setting the server address, then you are associating the file descriptor of the socket to the wolfSSL object with the secure SSL object, and then you will call wolfSSL connect. wolfSSL connect will start the handshake with the other peer. After the handshake, then you cannot use directly send to or receive from. And so you have to change them with encrypted send, encrypted write. And these are just wolfSSL write and wolfSSL read. And lastly, before closing the socket, you want to do some cleanup and housekeeping. So you want to notify the other party that the DTLS session is terminated. And you want to do some memory cleanup. So you call wolfSSL shutdown, you call free, and you free the object you used before. And then you are free to close the socket. So as you can see, there is some minimal amount of code change to transform the simple UDP application to use DTLS. If you can find a lot of more examples, several examples as well, you can find example based on lib event, example based on multi-thread in the GitHub repo provided in this slide in the DTLS directory. So feel free to check them. Okay, so just to summarize, DTLS 1.3 compared to DTLS version 1.2 provide you with a faster, with a server, safer, and with much more modern cutting-edge crypto. It required little to no chance for migrate to an application with UDP, from UDP to DTLS, or from DTLS version 1.2 to DTLS version 1.3. And of course, the beta version is already available in wolfSSL, where the first one, as far as we know, that we have a fully functional implementation of DTLS. If you're interested, remember that wolfSSL supports a broad range of microcontroller, operating system, and development environment. We are always available to answer technical questions. You can just write directly to support@wolfSSL.com. And don't forget, we are open source, so you can start evaluation and development of the right away of the DTLS and of the whole library right away. This ends my presentation so far, so I will be happy to reply to some question if you have it.
Okay, thank you for the presentation. We have one question queued up right now, so I'm going to read this one out. Why is there 3 functions in client and server examples have 3 functions in common before calling the function doing most of the work? Example server test, and then the 3 functions were start TCP, wolfSSL init, and change to wolf route or root. Sorry.
Okay, thanks, Marcus, for the question. So these examples are really very full-fledged example, full of features, and we use that also for our test suite, so for our continuous integration and stuff. So we needed to abstract most of the boilerplate code, like starting the socket, so starting the server, initting the context of wolfSSL, or we need to be sure that we are in the wolfSSL root directory and able to find certificate and key. And so you see a lot of this common function. If you are interested in more simpler and also easier to read example, you can find as you see in one of my last slide, you can go to wolfSSL example repos and you can find more of that.
Okay, thank you. Thank you for the question as well. We have someone raising their hand, so I'm going to unmute you.
Okay.
Hello.
Hello. Hi.
Yeah. Hi, this is Shankar here.
Nice.
Thanks for the presentation. I was just typing and I just realized that it's been unmuted. Thanks. The first question is, how many number of connections are supported, and what is the typical time taken during the initial setup time for the connections?
Okay, so thanks for the question. So this basically really depends on how you set up your server, your client. So you can support how many connections you want, and you can have basically usually have two different paradigms to do that. One is event driven, so you have like all your connection, your socket are not blocking, and you have a single thread that try to multiplex the time and try to do to go forward one or next connection one after the other, or you can have blocking socket and then you have multi-thread environment, so you basically move the burden of managing the time to your operating system. So there is no limit on the connection that you can support. The only limit, of course, is your hardware, your network, and your operating system. For how fast they are, of course, this also depends a lot on the latency of your network. Consider that an handshake, you will spend 2 round-trip time, and just 1 round-trip time will be above 1 kilobyte. That is the one with the certificate. So this should be really, really fast, and the overhead is really small. And of course, depends on your network.
Okay, so some benchmark indications that you can just give us inputs approximately.
So we didn't have any benchmarking numbers reported yet publicly because we are working on that. But of course, all of this is really open source, so you can literally compile the library with both versions and then just time DTLS 1.2 and DTLS 1.3. And if you have find any problems at all in doing that, you can always try to write to us. wolfSSL is really adaptable. You can compile it in a lot of ways. We have 3 math library because we support a lot of microcontroller operating systems. This is the reason why benchmarking for us it's a demanding task, and it really depends on what are you running your code. Okay.
Yeah.
That's the point.
Okay. So just one more follow-up question. Just like how you have a compatibility layer, suppose we already have a OpenSSL used currently. Is there a compatible FIPS compliant compatible layer for the DTLS part 2?
That's a great question. I suppose we have. And
You said you have?
briefly. Yeah, we should have. Let me check briefly because I was really in charge of DTLS 1.3, as you know, 1.3 is not supported by OpenSSL. So I didn't test any compatibility layer because there is no DTLS 1.3 in OpenSSL. But I'm checking right now if we have some this feature, and I'll let you know before the end of the Q&A.
Sure, no problem, no problem. Or you could communicate through mail too. That should be fine. Thank you.
Perfect. So I can email you.
Yeah,
Perfect.
you can go ahead and mute me. Thank you.
All right. Thank you for your question. Okay, we have another question. Will wolfSSL be responsible to create public key and certificate?
Okay, Henry, thanks for your question. No, we have the tools to create the public key and certificate, so you can create with our tools, and then you have to distribute yourself to the client and to the server. So we can do that, but we are not. We don't have any public key infrastructure to distribute this key, and of course you can use public key and certificate that are provided by other public key infrastructure.
Thank you.
Alrighty, we have a couple of more questions here. How much does the binary size increase when DTLS 1.3 is enabled compared to pure like DTLS 1.2 being enabled? I don't think we know exactly how much the binary size or like what the binary size changes between the two. However, I can say typically for wolfSSL, the range for our footprint size is between 20 to 100 kilobytes, depending on build options and the compiler being used. And so on like the average build, or typically on a build with an embedded and optimized compiler, build sizes with the full TLS 1.2 client and DTLS 1.3 will be around 60 kilobytes. If you want like a more specific example, I'd suggest you email us at support@wolfSSL.com, and we'd be happy to provide you with a more in-depth answer to that. We have another question here, which is, does wolfSSL DTLS 1.2/1.3 support hardware acceleration of AES SHA XXS with STM, with various different STM32s? And the answer is yes. We do support AES SHA as well as like a variety of other block ciphers and algorithms, specifically on the STM32 boards. If there's is a specific algorithm that we don't support, or like a specific board that you would like some hardware support with, then we're open to adding that support. So please email us at facts, that's FACTS @wolfSSL.com, and we'll be happy to help more in that regards. And we also have like a full list on our website, if you go and check, of specific hardware accelerations that we support with the specific boards as well. Can the API be used with static memory, specifically on embedded bare metal implementations? The answer is yes. So wolfSSL specifically, we're optimized for embedded devices, and we do put a special emphasis on bare metal applications. And so this API with the DTLS 1.3 support can be used with static memory. And again, if you would like some support or more information, please, go to our website or GitHub page and email us as well, and we'll be happy to provide more info. And we have one final question here. Does the product include an extensive set of examples, not just the one client/server one? So we have a couple of more examples, and that was provided in this presentation. However, I'm not sure exactly what you mean. I think we have like 3 examples currently, and we have like a basic client one, a basic server example, as well as an event-driven server example. If you'd like other examples or use cases, then I would recommend really emailing us at support@wolfSSL.com and see what other examples or information we can send over your way. And I think those were the last of our questions. Again, if you have any other questions or comments, as I've said multiple times already, please email us at facts, that's FACTS @wolfSSL.com, or even if you have like a more technical question, email us at support, SUPPORT @wolfSSL.com. And this webinar is being recorded and is available on our YouTube channel as well. And if you'd like to receive a copy of the slide deck, please email us at facts, that's FACTS @wolfSSL.com, and we'll be happy to send that over to you. Otherwise, I'd like to thank everyone for attending this webinar, and I hope you all have a fantastic rest of your day.